So let us start our course in trigonometry, which is measurements involving trigons or triangles. Of course, we will go much beyond only triangles, but right now what I'm going to do is I'm going to limit ourselves to even narrower portions, that is just a right triangle, and then we will move on to general triangles, then we'll move on further. All right, so here we have a right triangle. What it means is that one of the angles is a right angle, and for a right triangle we know that we have Pythagorean theorem, which tells us that, I mean, this part is called the hypotenuse. You may call these legs or, some other terminologies, which we will come towards later. So here, what we first have is that we have a square plus b square equals c square. So in this case, say we have a right triangle and we know any two of its sides. We can easily determine the third side or the length of the third side by using this Pythagorean theorem. For example, say we are given that this side here, say, is 5 inches and this is 2 inches. So say this portion is given to us, or we can obtain those portions. You can obtain C just by using the rule, that is C square equals 5 square plus 2 square, that is 25 plus 4, or C square is 25 plus 4 being 29. So C would be what? Since we are simply determining the length of the side. Okay, so what we will have is positive square root of 29, which we can use our calculator. That is, here is the square root of square root sign. So any calculator is similar. And then here we just type 29 and it gives us an approximate value. So say we are writing it to 4 digits after the decimal sign, then this will be 5.3852 inches. Okay, so 5.3852 inches. So that's approximate value of the hypotenuse, or C. Or on the other hand, we have the situation that we got a 22-foot ladder that is set against a vertical wall, and the bottom of the ladder is 13 foot from the wall, right? So here we have A equals 13 feet and C equals 22 feet. We don't always have to take them as A and C. And say we want to know how high along the wall is the top of the ladder reaching. That is, we want to know this portion B. And so what we have to do is pretty simple. We know by Pythagorean theorem that A square plus B square is C square. So A is 13. So 13 is square plus B square is 22 square. Now you can use your calculator that 13 square is 169, and then you got B square. 22 square is 484. Just feel free to use your calculator. So B square is 484 minus 169. So B square is going to be, we got 513. I am just subtracting the old-fashioned way. So B is the positive square root of 315, and now I shall use the calculator, or you could use the calculator to begin with. So we will just ask it for the square root of 315, and that is 17.7482 if we round to 4 digits after the decimal. So we have just a second, this quantity as 17.748 feet approximately. Okay, now let's go ahead and define functions for given angles of a right triangle. What I mean is this. So say we have this right triangle. As you can see, the measure of the angle ACB is 90 degrees. And let's look at the measure of this angle CAB. Okay, so here we are. So that's about 22.59 degrees. Now notice this, if I just, change the triangle so that all the sides are proportionately increasing, then the triangles are similar and the angle remains the same. Okay, and when the angle remains the same, say I did this, that I went ahead and measured the length of B, and say I measured the length of C, and then I went ahead and calculated their ratio. Okay, that is, I did B, okay, divided by C. All right, it turns out to be 0.38 approximately. Now what will happen is this, that is, if we change this this triangle to various similar triangles, then what's going on is the angle is the same and the ratio is the same, right? Even though the lengths of the sides are changing, but the ratio stays the same because of the similar triangle property. At the same time, say we did this, we changed the angle. You can see the ratio changed. But again, say we did the same thing again, the angle remains the same, then the ratio of B to C is the same. And the ratio of B to, if this side is A, B to A will be the same, A to C will be the same. So what happens is that among these similar triangles, these ratios, they do not change. So now what we can do is this. So say we have this right triangle, ABC. This is the right angle. And let's call this angle, or address it by a generic notation, theta. And let's let this side be B, and this side opposite to capital C is little c, and this is A. So if you look at this, then this side B is the side opposite to theta, right? That is, this is just a straight opposite to theta, okay? And this side A is, it's adjacent to theta, right? So you may call it, this is the adjacent side and that's the hypotenuse. So the way we define these ratios as this, and let's assume that at the moment our theta is between 0 and 90 degrees. Great. So let us define our trigonometric functions as, okay, that for theta, we define the sine of theta as B over C, or opposite over the hypotenuse. Cosine of theta as A over C, and tangent of theta as B over A, or opposite over adjacent, which is the same as sine theta over cosine theta. Likewise, now what we will do is that we shall define the reciprocal of sine as cosecant. So cosecant is the reciprocal of the sine, so it will become C divided by B. And then for cosine, we shall define the reciprocal of cosine as secant of theta. So here the reciprocal would be C over A. And then for the tangent, we define the cotangent of theta as adjacent over the opposite. All right. And this, of course, is 1 over tangent theta. All right. Okay. So, and this one, as I said, is 1 over cosine theta. So cosine and secant are reciprocal of each other, and cosecant and sine are the reciprocal of each other. Okay, so let's just do some little calculations with it or with these definitions. So what we will do is, let's take an example. So for instance, so let us now do some examples of calculations of these functions, in the right angle situation. So say we have this angle theta, and we got this right angle triangle, and this side, which is the opposite side, is B. This is the adjacent side A. So C will be what? Sum of the square roots of the legs or the perpendicular sides. So this would be square root of 5 feet. So if we have to get sine of theta, sine theta is going to be how much? That is going to be, I think I've gone a little out of our recording area. So here we are. So sine theta is, okay, opposite is 1, and hypotenuse is square root of 5. And we are not going to be that sensitive about it later on, but if you want, you can rationalize the denominator by multiplying both the numerator and the denominator by 5. And if you go for cosecant theta, which we write in like short by this, cosecant of theta, that's the reciprocal of sine theta, so here it'll be easier. So that's the square root of 5. If I go for cosine of theta, so that's the adjacent over the hypotenuse. So that's 2 over square root of 5. I'm just choosing not to rationalize the denominator here. Okay. And cosecant of theta would be what? The reciprocal, that is the square root of 5 over 2. And tangent is the opposite over the adjacent, so that will be 1/2. So cotangent, which is the reciprocal, that would be 2, right? So here is an illustration of these calculation of these functions for this triangle. All right, so let's look at this scenario where an observer measures the angle of elevation of the top of a vertical tree 80 feet horizontally from the bottom of the tree. So this is 80 feet, right? And here is observer. Okay. And this is the bottom of the tree. This is the top, this is the bottom, and this angle is measured as 27.3. And in practice, there are ways to measure these angles, such as this instrument clinometer. I have downloaded it on my iPad, so you can just see that what the inclination of a point is, or that line is. All right. So let's not go in that part too much in detail. So with that surveying done for us, what we have to do is we would like to find the height of the tree approximately, or it didn't ask for how many digits we have to approximate. So let's just go ahead to say the nearest whole number. All right. But on the test, you will be given how far to approximate. So if you look at this h is the opposite side and 80 is adjacent, and opposite over adjacent is how much? That's the tangent of the angle. All right. Okay. Now, what we will do is that we will calculate the tangent of this angle, which is given in degrees by using our calculator. Okay, and once we do that, and again, our angle is in degrees, and calculator has these functions, and this is the calculator that we are using in this course. So let's put the mode in the degrees because right now it is in radians, which we will go over probably next week. Okay, so here we put that in degrees, and then what we want is we want tangent of uh, 27.3 degrees, right? So that's simply 0.5161, or we can see this here. We can write this as 0.5161, or right here we can observe that if we multiply the equation both the sides by 80, then this becomes h becomes 80 times tangent of 27.3 degrees. Okay, and we can get that 80 times. We can go second answer or just write tangent again because we are still in the degrees mode, and then this comes out to be 41.29, and if we go to the nearest whole number, then that is approximately how much? 41 feet, right? So that's what approximate height of the tree is to the nearest whole number. All right. So as another example, let's take up this scenario in which a particle is traveling along the circumference of this half circle. All right, and you may remember from high school geometry that this angle is always, or the angle BPA is always a right angle. So here we have a right triangle. All right, so this always subtends the right triangle. Now say we are able to measure this angle and we want to measure the distance. So for example, so say here we have a particular scenario in which this angle is given to be 24.56 degrees, and this side is 10 feet, and this is right angle as we just mentioned. Then we would like to know what the distance from A to P is at the instant when this angle is 24.56 degrees. So you can see this 10 feet is the hypotenuse. We have to find the adjacent, and we know that adjacent over the hypotenuse is going to be cosine of this angle. So that will be cosine of 24.56 degrees. So A would be how much? 10 times cosine of 24.56 degrees. Now we can bring our calculator back, okay, and we can go for 10 times. Remember, we are still in the degrees mode because I didn't change anything in between. So 0.56. So it's like about 9.1 actually, approximated to one digit after the decimal sign. So it's about 9.1 feet, the distance from A to P. All right. Now let us look at a feature of our calculator which we are going to directly use, and this is a very basic trigonometric course, so I'm doing it really very much out of order. In pre-calculus you will learn it at appropriate place. So what I mean to say here is this, that if you look at here in this portion there are sine and sine inverse, and what is meant by this is this, that if say sine of Say for example, let's see what sine of 30 degrees is. So here we have sine and we are in degrees mode. You can see sine of 30 degrees is 1/2. So if you apply this function on this 1/2, the value of sine of 30 degrees, let's see what it gives us. Okay, so here I went second this because that's what will bring sine inverse for us. 1 over 2, which is zero point 0.5, of course. What do I get? I get 30 degrees. So what we do is this, that we use these features to do the inverse calculations. So for example, say to find theta such that, say, tangent of theta is, I'm just taking any number. I just, took a number 2. You could have taken another number. So then what theta is going to be? Tangent inverse of 2. All right, so how would we get that? We'll go right here, tangent inverse 2, and that's going to be about 63.43 degrees. Okay, now remember this, here we are limited to sine, cosine, and tangent. It doesn't give us the reciprocals. So say I have to do this. That is, I want to find the value of theta such that secant of theta is 3. Now there is no secant key on the calculator, but there is cosine key, and I know cosine is reciprocal of secant. So what I got is that cosine of theta is reciprocal of the secant of theta. So that's going to be 1 over 3 because this is 3 over 1. All right. So theta would be how much? Cosine inverse 1 over 3, and we are in degrees mode, so it will give us the answer in degrees. Okay, and there we are. This is about 70.53 degrees. Okay, and we shall do more of these calculations in the applications because this is a special course in which we are just learning how to do most trigonometry mostly by calculator. Okay, and but still let's take a non-calculator side just for a few minutes before I finish this lesson. So let's take a very special triangle, which is an isosceles right triangle. That is, uh, these two sides are congruent. So let's just assume that both of them are, their lengths are 1 unit each. So the hypotenuse would be how much? And say we call these as A, B, C. So the hypotenuse will be square root of 1 square plus 1 square, that is square root of 2. Now, for an isosceles triangle, these two angles will be congruent. So this is 90 degrees, and the three angles add up to 180 degrees. So these will have to be 45 degrees each. So what we just did was that this is a special angle 45 degrees. Now we can go ahead and look at this triangle and write all these values easily. That is, sine of 45 is 1 over square root of 2, right? And again, I'm writing it only for sine, will not worry about the others. So square root of 2 over 2. Cosecant would be the reciprocal, and that will be the reciprocal here. That's a square root of 2. Cosine of 45 degrees in this case turns out to be the same. Adjacent is also 1. So it's 1 over square root of 2. And secant of 45 degrees is going to be square root of 2. And tangent is going to be a real easy deal because here if you look at the opposite over adjacent, it's 1 over 1, that is 1. So the cotangent of 45 degrees is also 1. So if you look at the notes that I wrote for you, I have listed these angles in a special part for you. All right. And so this was one special triangles. Let's take just one more special triangle and then conclude this lesson. Okay. Now let's take another special triangle, which is 30, 60, 90 degrees triangle. This angle C is 90 degrees, the angle B is 60 degrees, and the angle A is 30 degrees. Now notice here that if we do this, if we reflect this portion by this, then what will happen is this turns into an equilateral triangle because it's just the reflection. So these two sides are congruent. This is common, and these two sides are congruent. So this now becomes a becomes an equilateral triangle. And let's work on it and get the trig functions for the trigonometric functions for the 30 degrees and 60 degrees angles. So now that we knew that the angle here is 60 degrees, this angle is 90 degrees, we got 30 degrees, and then these triangles are congruent, so we got 30 degrees, 60 degrees, and then this 90 degrees again here. So what happens? This triangle becomes an equilateral triangle. So all these sides are congruent, and so what we notice here is this, that this and this are going to be congruent, and this entire side is same in the length as this entire side is. So if we go ahead and let's just remove this part. We are done with this for sake of our discussion. So what we notice is this, that this side here, or this side here, is going to be half of this side, or this is going to be twice this side. So there are two ways we can do this. One is this, that is, now we know that the ratio of these guys is 1 to 2. So I can take this side as 1 and this side as 2. So what this side will become? This is the side B. So remember this, a square plus b square is c square. So here 1 square plus b square would be 2 square, or b square would be, this is 4. So when you take 1 to the other side, 4 minus 1, 1 will be 3, or once again b square is 3. Now the length will be the positive square root of 3. So this becomes positive square root of 3. So if you look at the angle 60 degrees, then what do you notice? That sine of 60 degrees is, opposite is the square root of 3, and adjacent is 1 over 2, while cosine of 60 degrees is going to be, adjacent is 1 and hypotenuse is 2. Or if I go to this angle right here, what you notice is that sine of 30 degrees is 1/2, which is the same as the cosine of 60 degrees. And if you look at cosine of 30 degrees, then the adjacent is the square root of 3. So that becomes a square root of 3 over 2. So here what you have found is, and these are some standard values and you keep these special triangles in mind, then these values are not really very hard to retain. That is, I'm just rewriting those. And cosine of 60 degrees is 1/2. Sine of 60 degrees is square root of 3 over 2, right? And actually here I meant to write that cosine of 30 degrees is the square root of 3 over 2. And you can go ahead and find the values of tangent, cotangent, cosecant, and secant likewise. So let's just note a last point and then we will just conclude this one. All right. So notice one property here, that is, you know that a is square plus b square equals c square for a right triangle like this. Now, if we divide by c square, what we get is that a square divided by c square plus b square divided by c square will become 1. And what is this quantity? This quantity is square of the cosine function because a divided by c is cosine of theta. Likewise, this is the square of the sine function. Now, the way we write is this is this, and that is just a custom. That is square of cosine theta is written as cosine square theta. Okay, in this manner, it's not cosine of theta, it's cosine of theta times cosine of theta. So this is also called Pythagorean identity, that sum of the squares of cosine and sine of the same angle that equals 1. And let's notice just one more property here based on how much we have done. This angle is 90 degrees minus theta, right? So notice this. If I write sine of theta, that is b over c. Now, if I write cosine of 90 degrees minus theta, then what that is also b over c because b is adjacent to 90 degrees minus theta. So that is also b over c. And at the same time, you can see cosine of theta is a over c. While on the other hand, if I went ahead and wrote uh, that I think I wrote this out of the recording area. So cosine of theta is a over c. And if I write sine of 90 degrees minus theta, okay, then that is also a over c because a is opposite to this angle. So here are two identities that we have. One is sine of 90 degrees minus theta is the same as cosine theta, and cosine of 90 degrees minus theta is the same as sine theta. And we shall use it every now and then. So it's a good, it's a good thing that we are able to deduce these two properties based on our discussion in this lesson. All right.